This is the second part of the lecture on shock boundary layer interaction, and today's topic is oblique shock impingement on a flat plate. The geometry is again very simple. If we have a plate of this kind and we have a oblique shock coming from outside, for example this, impinging on the flat plate, and it will get reflected, something of this kind. This shock can be generated by another body or a different part of the same body, and we will see some specific examples shortly. But let me put a small wedge here, which is generally used as a shock generator if it is this flow is to be studied in an experimental setup in a wind tunnel. So we have supersonic, hypersonic flow coming in. Conditions are corresponding to station 1. Across the shock we have station 2. Pressure rises, density rises, velocity decreases. Let me place it slightly differently. Oops. And the reflected shock gives another pressure rise. So the flow goes from being horizontal like this to an inclined flow because of the first shock, and then again is turned horizontal by the second shock. If we think of this as an inviscid picture and try to plot the pressure distribution along the plate, it would be again fairly straightforward. The pressure is equal to the pressure value P1 up to the point where the shock impinges, and at that point there will be a sudden jump in pressure and it reaches value P3. The effect of both the incident shock that is coming in and the reflected shock are felt at the single point, which is the point of shock boundary layer interaction. Now this kind of thing is very common in what's called multi-body aerodynamics. For example, if there is a rocket with strap-on boosters, the shock generated by the tip of the booster, for example here, can impinge on the body of the main rocket, and there are situations where the main rocket actually houses fuel tanks in the regions where the shock impinges. So this as shock boundary interaction becomes quite important in such scenario. This can also occur when, let's say, you have an aircraft which has missiles or other projectiles under its wing. So the plate now becomes, if you flip it around, it becomes the underside of the wing, and the shock wave in a supersonic flight, shock wave generated by the projectile, let's say missile, will impinge on the can impinge on the underside of the wing. Another example which is very important comes up when we have engine intakes. Sorry. Engine intakes in supersonic and hypersonic flows. And intake, if you're inside, and we know that high-speed intakes use shock waves to compress and compress the gas. Inside the duct, intake duct, there can be multiple shocks bouncing back and forth between the walls. So this could be a scenario where shock from one side of the intake reflects from the other side of the intake. Okay, now the inviscid picture that we have drawn here is possible. It can be seen in situations where the shock wave is not very strong, so that the boundary layer that comes on the plate does not separate and so still remains attached. So the picture, the shock topology is very similar to what we have drawn as inviscid. But when we have strong shocks and the boundary layer separates, we have a very different and complex flow topology. So let me draw that. I need a bigger picture. I need to make a bigger picture, so let me try it this way. Here is the large, a magnified view of the plate, on which we have a turbulent boundary layer. Velocity profile shown by this. And now we have the oblique shock coming in at a point like this, and the reflected shock is here. Now the adverse pressure gradient of the incident and the reflected shock together is most often high enough to separate the boundary layer. So we will get, let's say again try to make a magnified view, a picture which looks like this. We have a separation point S, where the flow, the boundary layer coming from the left gets separated from the surface, and the flow takes off over the separation bubble. It goes around and reattaches on the plate. We have reattachment point R, and in between the S and R is the separation bubble, where we have some kind of a vortex structure. Now the inviscid impingement of the shock was somewhere near the reattachment point, and the separation bubble forms upstream of that point. Now if you think about supersonic flow, so let's say this flow in region 1 is supersonic, we can kind of say that information travels only downstream. Is because the flow velocity is higher than the speed of sound, no information can travel upstream in the flow. So the question becomes, how come the separation occurs before the inviscid shock impingement point, before the flow, before the supersonic flow comes to know about existence of the shock? How can it separate? So that has been a kind of a confusion, and it is resolved by noting that even in a supersonic flow, there is subsonic region in the boundary layer. So if you look at the boundary layer profile, out at the edge, Mach numbers greater than 1, velocity is high, but as we come to the wall, we have no slip, 0 velocity, so there must be some region where velocity is less than the sonic speed. So that through that subsonic region, information can travel upstream, and what we get is that the separation point is comes before the inviscid shock is encountered by the boundary layer. So it is called upstream influence. And in an experiment or in a flow like this, or even in CFD, we try to measure the extent of upstream influence. How far is the point S, separation point, where the bound layer gets detached from the surface? How far it is upstream compared to the inviscid shock impingement. If there was no boundary layer, we can extrapolate this shock and see that it will impinge somewhere in this point, which we are now calling, it's somewhere near R. Okay. Now, once we have a separation bubble, it acts as a kind of a blockage in the flow, and the flow has to go around it, and that's what we've drawn here. Anytime a flow has to turn, a supersonic flow has to turn, it has to generate a shock wave. So now the shock structure also changes because of the separation bubble. It does not remain like what we had in an inviscid scenario, in single shock coming in and a single reflected shock going out. So that, let's draw a picture of the shock structure. Again, a magnified view, because there are many more things to show. Okay, this dashed region I'm going to use to represent the separation bubble, the vortex that is trapped inside. Flow coming in from the left has to go through a separation shock S, which meets the incident shock I, and there is a shock-shock interaction. When two shocks of this kind meet, they generate two additional shock waves. Here is the one, and here is the other. Now the flow goes over the separation bubble and then has to go through this shock and then turn around. In a way, it has to expand. It has to go around a corner, which can generate expansion waves. And then the flow has to go and reattach, where it generates the reattachment shock. Now the expansion fan E interacts with the shock that is generated from the what is called a triple point here, and that curves this shock wave. And it intersects with the reattachment shock. One more shock-shock interaction, which generates the reflected shock. Okay, so now we have not just a single incident and a single reflected shock, we have a large number of other shocks and expansion waves, and we do have shock-shock and shock expansion interactions. In addition to shock boundary layer interaction, which generate the separation bubble in its first place. So things are getting a little more complicated. Now, let's see what the pressure and skin friction looked like in a flow like this. I would draw pressure on the left hand side and skin friction, the second plot. We have P, CF, both are plotted as function of x, x being the distance along the plate. Pressure remains at undisturbed P1 condition until it hits the separation point, at which it rises because of the separation shock. And in the separation bubble between S and R, it attains a kind of a uniform value, which is called the plateau. And then near reattachment point, it again increases to reach the higher pressure, P3. Reattachment point is somewhere here. So the pressure plot looks very similar to what we saw earlier for a compression corner. There is separation shock, there's reattachment pressure rise, and there's a pressure plateau in between. The only difference compared to compression corner is it goes from P1 to P3 instead of P1 to P2. Okay, now the skin friction plot also has a very similar pattern as compression corner, and that is done by let me move the axis to a point where it is, let's say 0 is here. We start with skin friction value, which is for the boundary layer coming in from the left, and then at separation point it goes down, crosses 0, and that's the definition of separation point, which has skin friction going from positive to negative. It has a pattern something like this, and then it goes from negative to positive reattachment and goes to high value behind the reattachment point in the flow when it starts recovering back from this interaction. CF increases, takes high values, and heat transfer also has high values in the reattachment and post-reattachment region. So 2 points to note here. One is very similar. The pattern is very similar to compression corner. Compression corner, compression ramp. And the second thing is we have high heat transfer, which I have not plotted, but that is something to note. High heat transfer at reattachment. So now, if we go back to the scenario where we explained that the shock wave, oblique shock that is coming in and impinging on the plate can be generated by a booster rocket, and that impingement happens on the main body of the main rocket, which can house propellant and oxidizer tanks. This high heating at the point of shock impingement can be a major concern to save and protect those fuel tanks. There is one another aspect which is also very crucial for such shock boundary interactions generated by oblique impingement, that is blockage, flow blockage in an engine inlet duct. So I'm going to take the picture that we had drawn initially and extend it a bit more. Something of this sort. Let's assume that this is one side of the engine, and this is the other side. We can visualize this as the lower side being part of the fuselage, and there's an engine intake on its side, which is, then this happens to be the cowl tip. Shock flow coming in, supersonic flow, can be hypersonic flow, and that generates a shock wave from the cowl tip. It impinges on the other side of the engine duct and reflects back. Boundary layer on the engine wall can generate a shock boundary interaction where the impingement happens, and we can get a separation bubble of this kind. I will skip the remaining details. Of course, there will be additional shock, separation shock, expansion fan, and so on. So the flow field is fairly complex. But even if I leave those details out for now, the most important thing to note here is that we have to make the flow has to go around this blockage, around the separation bubble. So we have, in effect, we have a smaller region of the duct that is now open to the flow that has to go into the engine. Now this region can actually, if you can imagine, it looks like a duct that is converging in its cross section up to a point where where we are at the top of the separation bubble, and then it is diverging again. So the smallest area looks like a throat, at which, if the conditions are such that, can have choked flow. And choked flow means that it restricts the amount of air that can go into the engine. And that can lead to situations which are called unstart, and the engine intake fails to deliver enough airflow into the engine, the thrust comes down, and the whole engine operation can stop. Now, it's easy to see that entire thing, whether it chokes or not, and whether the unstart happens or not, depends on the size of the separation bubble, in some scenarios, in hypersonic for scramjet kind of application, the separation bubble can be as big as 25, 30, 35% of the intake duct height. So you're blocking off 1/3 of the engine by having a SBLI, shock bound interaction, inside it. And if it happens such that we need to know that a priori, so that during operation we can account for it and make sure that the engine does not stall, does not unstart because of that, what we need our CFD tools to predict should predict the separation bubble size accurately. And this happens to be a major challenge, especially when the flow is turbulent, and that leads to a whole area of research where people are trying to develop tools which can predict the size of flow separation in shock bound interaction accurately. With that, we'll stop here. Thank you.